I will talk about the topological defects in the early universe. So, yeah. So first of all, I will talk about the homotopies in the mathematical point of view, and discuss the general um, explanation for the topological defect, and I will turn to the example for the monopole cosmic touring domain wall and the other objects. First of all, the topological defects, there is some solutions which has a topologically stable configuration of the given gauge Higgs field, and such a topological defects appears after the spontaneous symmetry breaking. And there are some similar objects, but for the non-topological solution. Even though this is non-topological, but this is stable. There was some conserved global quantum number, and this gives us stability. Example is the cube or solution star. And the tax, also this is a similar object. This is a topological configuration after spontaneous symmetry breaking, but is unstable. For instance, over the tax's transition solution, like the instantiums occurs. So we can classify such a table. Topological defect is a topological stable solution, and the solution is non-topological but stable, and texture is topological unstable configuration. So now let's consider the mathematical point of view. If we assign the group C as a symmetry, and it is spontaneous symmetry broken to the H's as a remain unbroken symmetry, then the degenerate vacuums are given by the quotient group 0 by the H's. The H's is some the symmetry for the unbroken symmetry, and we can assign the some vacuum V. And if we ask the some elements of the broken symmetry which is not included in the H's, then it turns to the other vacuum. Because this G1 is the elements of the broken symmetry, so the V prime after acting on the G1 is includes it in the other coset. So if we collect this all the cosets, we can obtain the generator vacuum. This is because the definition of the spontaneous symmetry breaking is a vacuum state is not imbalanced under the broken symmetry transformation. So this vacuum state is not imbalanced under the broken symmetry transformation G1. So this gives the other vacuum V prime, and if we collect all the cosets, then we can obtain the generator vacuum collections. And under such a spontaneous symmetry breaking, there exists the degenerate vacuums that are the quotient group 0 by H's, and we want to obtain the finite action solution or finite energy solution. So to obtain such a finite energy, we should assign the from the spatial infinity to the some vacuum state. The spatial infinity is usually given by the end sphere. And we should each point map to the vacuum state in vacuum structure, such a manifold geodesics, and this mapping can be classified topologically. So here is some of the mathematical point of view. In the topology, we can define the path as a continuous function, and if the starting point and end point is the same, this is called a loop. And we can define the equivalent relations, which is called homotopic. Two paths are homotopics if the two paths continuously deformable with each other. That are defined by if there's the existence of the continuous map H's, or when the parameter t is equal to 0, so it is the same with the p. But if the t equal to the 1, it's the same with the p prime, or the second path. So if we define such homotopic relation, this is the equivalent relation, so we can define the equivalent class. So by using the equivalence class, we can define the cosets as a loop path, and if this app is a mapping from the spatial infinity Sn to the some manifold X, then if we collect such a cosets, then this is called homotopy group. So X is a manifold, and N is called some spatial infinity Sn. So the definitions of the homotopy again. the mapping up from the Sn to the X manifold, and if we collect all the cosets under the homotopy equivalent relation, then this is called anti-homotopy groups of the manifold X. For example, so if we consider a very simple and trivial example, as pi ones and one homotopies of the first homotopy groups of the R scales trivial. Because all the loops is under the R scales, they can be deformed over each other. So the R scales it is just simply connected. But if we consider S1 such a manifold, just a circle, then depending on the winding number, for example, the one counterclockwise or two counterclockwise, or the clockwise winding or two clockwise winding or zeros winding, such a path cannot be continuously deformable. So there are some several mapping is possible. So the pi one means that the mappings comes from S1 to the manifold S1 here, this S1, and this one go to here. So that there are several mapping is possible, and such a path is such a different mapping is not homotopy is the other. So if we collect all the loop paths, then we can obtain the first homotopy groups of the S1. This is the integer, which represents sort of the winding number. So in general, the n homotopies or same groups are given by the jet and also is given by the not jet and jet integer number, and this is called about S2. In this case, the winding number is generalized through the point triangle index. And if the manifold is a more complicated structure, so if the integer m is larger than n, then this becomes a trivial group. In the physical point of view, the special infinities as assigned to the each vacuums for the each mappings of the coset. So that if we rearrange sort of the field configuration, it requires an infinity energy. So that it is impossible. So it ensures the stability by the topological invariant quantity. Now I will talk about the physical point of view. The topological defects are produced in the early universe after the phase transitions at the critical temperatures Tc. So after the cooling, T is below than the Tc. The spontaneous symmetry breaking circle and the topological defects exist. And the number density of these topological defects is given by the Boltzmann separations at the critical temperature. This is a case of the thermal production, but usually the mass of the topological defect is extremely larger than the critical temperature, so the production is insufficient. So there are some other production mechanism, which is the Kibble mechanism. There is a Hubble parameters H's, and the Hubble regions are given by the H inverse as Hubble patches, size of the Hubble patches. So the inside of this Hubble region, the build configuration is causally connected. So this is the configuration of the correlated each other. So let's consider the two Hubble patches, the ones V1 and V2. And if the partial scales of the build configuration is larger than this Hubble patches sizes, so in the Hubble region 1 and Hubble region 2, they are not correlated each other, but the spatial scales of the build configurations, LTD, is rather than Hubble patches, so the topological defect can deform. So this is called the Kibble mechanism. So, and at least in the Hubble volumes, there's one topological defect that is produced. So that we can bind the lower bounds of the number density of the topological defects, and the Kibble mechanism is given by the 1 over the H is the inverse volume. And we know that the Hubble parameters in terms of sort of the temperatures, and it occurs around the critical temperature. So this is the lower bounds of the number density sort of the topological defects and the Kibble mechanism. Now we turn to some several examples of the topological defects briefly. So first example is monopole. The simple model is acid gauge theories. There are Bill strengths and scalars gauge interactions and the scalars potential. And after the spontaneous matter breakings, the perhaps is non-zero valve is fixed. So there will be some massive gauge boson and massless boson setup here. And in this case, the SU2 gauges that are broken to the U1 broken, U1 gauge symmetry, unbroken symmetry. So the Becker manifold is given by the quotient groups of the SU2 over the U1. This is equivalent to the S2. Because S2 is given by the ball with the 3D rotations, there are 1 degree freedom in the angle and the 2 degree freedom in the direction. And the U1 is given by the radius as the radian angle. So the SU2 of the U1 gives just the SU2, which is the Boy's sphere. And we want to obtain the static field configurations and the finite energy solutions. So there's no time dependence here. And for the energy, to have the finite energy, the partial infinities at the x go to the infinities that is given by the S2 should match to the vacuum. So the in the topological classifier, this is the second homotopy group of S2, which is given by the integer group. And there is an example of the solutions with the scalar field and the gauge field for the R go to the infinity, some function go to the zeros as a symptotic behavior, and around the zeros also this gives the for the R go to the infinity, some energy is the proportional 1 over the R. So the energy is the asymptotically placed in the partial infinity, and depending on the each region's arrows, so we can classify the monopole as an anti-monopole. And such a monopole can be the related magnetic monopole with the one of the asked behaviors of the magnetic field from the field strength, and there will be the magnetic monopole charges. And there is a cosmological monopole problem, and we can obtain the number density and the energy density, and if we consider the monopole anti-monopole annihilation is negligible, and the monopole entropy relative is almost constant, then the we can calculate sort of the monopole energy density by using the monopole entropy relative, and we can install some critical temperatures and the mass of the monopole as a typical case of the GT. Then this is very large, 10 to the 12 GB over the cubic centimeter. This is extremely large compared to the critical number density sort of the universe 100 minus 5 CV over the cubic centimeter. And even though if we include the annihilation sort of the monopole anti-monopole process with the cross sections sigma as a z both over the t square at the some specific without temperature, still the monopole imbalances in the current universe is very large. This is 10 to the some numbers rather than the critical number density of the universe, and this requires some of the delusions by the impulsion theory. The next example is the cosmic string. This arises from the some U1 symmetry broken. So we can also obtain the topological classifications. The first homotopy groups of the U1 given by the jet. So there are some of the minimal abelian Higgs model. U1 symmetry is broken with some non-zero fixed back expectation value. And the pi series continuous, the string is always closed or infinite. And also we can obtain the solutions of the pi and the gauge version fields a mu. And also we can obtain the string energy per unit length, which is defined as string tension mu as the jet, and that is given by the pi v scale. So the v is a Bath scale, and we assume that the winding numbers are equal to the one here. And we can calculate the some equation of the state of the such a cosmic string. Equation of the state, which means that the relation between the processor and the density is in the cosmology, and this depends on the string velocity. We can compute the average of the stress tensor T mu as such a form depending on the velocity and the cosmic string tension obtained by the such average over the 2D plane. And the relation between the pressures of the string and the energy of the string is given by the functions of the string velocity. So if the strong velocity is very slow, Vs equal to 0, in the units of the speed of the light. Then the equation of the star is minus 1/3. And the anode density is h to the minus 2. This is curvature-like. But if the Vs, cosmic string, velocity is 1/√2 c, then the equation of star is 0, so the lower h to the minus 3. This is the matter-like. And if the Vs is almost 1, speed of the light, and the equation of star is 1/3, and this gives h to the minus 4, almost radiation-like. So depending on the cosmic strings, the equation of the star is different. And here's a few remarks. The string can give the double image like the gravitational lensings, and also the source of the CMB and through piece as the gravitational three part. The final example of the topological defects is the domain walls, which comes from the symmetry breakings of the discrete symmetry like the Z2. This is a very minimal example of the Lagrangian, so we can fix the path, and the manifold, the general temperature manifold is given by the Z2. So the topological homotopy graph is also given by the Z2. And the solution can be obtained by the analytically. It is a tangent hypers, and the deltas give the energies and thickness of this domain wall. There's a king solution and anti-king solution here. And also we can calculate the surface energy density as a function of the lambda and the v. And to avoid the cosmological problems of the CMB, and this surface number density eta should be smaller than the 1 MeV scales. This is the main problem. The final remarks, there was a texture which is the topological but unstable. This also produces after the spontaneous symmetry breaking over to the O1 with such a Lagrangian. And because the energy density term is entirely gradient term, this gives the rho 1 the axis the replaced by the alpha axis with the small alpha. So this is unstable. So the after the shrinkings, the such a texture structure disappear. And there are one more things in topological but stable solution QL, which comes from the control of the global charges. This is examples with the global U1 charge symmetry. So today, we talk about the topological defects with the point of mathematics and the productions of the on the early universe and the cosmological problems here.